In this video, we will see about resistance and what is the temperature coefficient of resistance. So let us see about conductors and insulators. What are conductors? These materials which allow current to pass through it are called conductors, whereas the materials which does not allow the current to pass through it are called insulators. So easily you can pass the current through conductor, whereas insulators you cannot allow the current to flow through it. Now let us see about the resistance. You take a night lamp and connect it to a circuit. We know that this bulb always consumes very less current. The current drawn by this bulb is very less. Suppose if I take a 100-watt bulb and connect it in the circuit, the current drawn by it will be very high compared to this bulb, night lamp. So why is it so? If you see the resistance of this 15-watt bulb, it will be very high compared to the 100-watt bulb. So it means that if you have a high resistance load connected in your circuit, the current drawn will be less. And when you have a low resistance, current can flow easily, it takes more current. So the resistance is opposition offered by a substance to the flow of electric current. Next we will see the unit of resistance. So the unit of resistance is ohm. It is named after this scientist George Simon Ohm, who invented the Ohm's law. And this is the symbol of the resistor, which we will use it for drawing the circuits, and this is the resistor which we normally use it for small mini projects. This is a half watt resistor. Half watt, quarter watt will be like this, small resistors. Let us see what are the factors affecting the resistance. So suppose you take a copper strip, so that is connected to a voltage source, and the resistance of this strip is R and the length of the strip is L. Okay. Now as voltage is connected here, current will flow through this circuit. Suppose I am increasing the length of this copper strip now. So if I increase the length, what happens? The electrons has to flow over a long distance now. So initially the distance was small, so the resistance for the flow of electrons is less. Now the length has increased, so the resistance will increase. For example, if you take a heavy traffic lane, if the length of the traffic is high, you need more time to reach your destination. Similarly here, as the length of the strip increases, the electrons has to travel a long distance and its resistance will increase. So we can say that R, the resistance, is directly proportional to the length of the strip. Next, let us see the next parameter, which is the area. You see, compared to this, the area of this copper strip has increased. So as the diameter has increased, area increases. So when area increases, you have more space for the electrons to flow. So you compare to the traffic, here you are traveling in a single lane, so it takes more time to reach the destination. Here you are traveling in a 4-lane, so naturally what happens? You can easily reach your destination, or the resistance offered will decrease. So R is inversely proportional to area. So R is directly proportional to length and inversely proportional to area. So I can write R is equal to rho into L by A, where rho is called the resistivity or specific resistance. So this rho depends upon the material. What type of material we are using for the current conduction. Now let's see about this specific resistance. We have seen that resistance is equal to rho L by A. So what is rho? Rho is equal to R into A by L. So R is in ohms, area will be meter square divided by meter. So the unit of resistivity or specific resistance is ohm meter. So the specific resistance or resistivity of any material, rho, is a constant for one particular material and its unit is ohm meter, and it depends upon the nature of the material. So in addition to these three parameters, the resistance also depends upon the temperature. So as the temperatures in some materials, the resistance will change. Now let us see about conductance. So conductance is the reciprocal of resistance. So the symbol is same, but instead of that we will write G is equal to 1 by R. So this R represents resistance, whereas G represents conductance, that is equal to 1 by R. So this conductance will be specified in some of the parallel circuits so that it will be easy to simplify these circuits. So the unit of conductance is Siemens, or earlier it was called mho. That is, you write the ohm in opposite direction, you will get mho. And the symbol is also just inversion of ohm. So earlier this symbol was used, but you can use Siemens, yes. G is equal to 1 by R, where R is equal to rho L by A. So you substitute R value here. So G is equal to this one, and this 1 by rho is given by sigma. This sigma is called the conductivity or specific conductance of the material, and its unit is Siemens per meter or mho per meter. So let us solve one small problem. Determine the resistance of a 1 kilometer copper strip whose cross section is 2.5 centimeter by 0.05 centimeter. Assume rho is equal to this one. So first let us write the given data. So what is given? Length is 1 kilometer. So 1 kilometer, always remember, question is very easy. Only thing is the unit is not in meter. That you should take care of. You take care of all the units. So you have the formula only in meter. So convert it to meter. So 1 kilometer is equal to 1000 meter. And rho, it is given in meter. So no problem. And area is equal to 2.5 into 0.5. See here it is given in centimeter. So convert this to meter by multiplying by 10 power minus 4. Now apply the formula rho L by A. Substitute all the values, you will get the resistant value. So the problem is very simple, direct application of formula. Only issue is you take care of the units. Let us come to the second topic, the effect of temperature on resistance. So we know the temperature continuously changes and it varies with respect to the location. For example, you take a machine which is not running. You can go and easily touch the machine. But after it is running continuously for 2 or 3 hours, if you go near the machine, you cannot touch it because it might get heated up. So you can feel the temperature difference there. So what happens to the resistance of the coil when it is continuously running for 2 or 3 hours. What happens to the resistance when this temperature increases? That is what we are going to see now. So this temperature changes the resistance of the material. So there are materials whose resistance changes with respect to temperature. So it can, in some material the resistance increases, and in some material the resistance decreases with increase in temperature. So if you take a conductor, so the graph is between resistance and temperature. If you take a conductor, as the temperature increases, resistance will also increase. We know that when the resistance increases, current will decrease. This is what happens in a machine or motor. What happens? Initially, the resistance will be less, so current will be more. After some time, when the machine starts to run, it gets heated up. Now the temperature, as the temperature increases, the resistance will increase. If the resistance increases, current will decrease, so that the machine or the winding will not burn out. So that is why conductors will be used there. And if you take an insulator or a semiconductor, as the temperature increases, the resistance will decrease. So this also you can experience when you have a wire with an insulator, and if it is exposed to sun or high temperature for a long time, the insulator slightly start to break out. So depending upon the temperature, the resistance may increase or decrease. So we have seen that some materials the resistance will increase, and in some materials the resistance will decrease with respect to temperature. So the materials in which the resistance increases with increase in temperature are said to have positive temperature coefficient of resistance. Example, copper and aluminum. And some materials have negative temperature of coefficient. It means that its resistance decreases with increase in temperature, like insulators. So you have positive temperature coefficient materials as well as negative temperature coefficient materials. So we have already seen that as the temperature changes, the resistance changes. Suppose at 0 degree I know my resistance, but at this the temperature changes or increases. The motor is running and its temperature increases. Now I cannot go and measure the resistance because motor is running. Its temperature has increased. So I need some formula to calculate what will be the resistance at different temperatures. Because for a machine I can measure the temperature from outside, but resistance I cannot measure. So I need some formula. Let us see about that. Now let us take a copper strip whose resistance at 0 degree is R0, and suppose let us take this machine. It is running for some time, so its temperature increases to T degree, and at that time its resistance is RT. Okay, so what is the change in resistance? RT minus R0, because this is the final resistance, this is the initial resistance. So this change in resistance del R depends upon what is the initial resistance and what is the change in temperature. So I can write del R is directly proportional to initial resistance as well as change in temperature, that is T minus 0. I have taken it as T. So R0 into T. So this one I can write it as alpha naught R0 into T, where this alpha naught is called the temperature coefficient of resistance at 0 degree Celsius. So this 0 represents that this value is at 0 degree. because at each degree this value will change. So alpha naught depends upon the nature of the material as well as temperature. So let us see what is the temperature coefficient of resistance. So we have already derived change in resistance is equal to alpha naught R naught into T, where R naught is the resistance at 0 degree, RT is the resistance at T degree, and alpha naught is the temperature coefficient at 0 degree. So what is change in resistance? RT minus R naught. So that is equal to this one. From that you can find RT. So using this formula, you can find the resistance at any temperature if you know the resistance at 0 degree as well as what is the temperature coefficient at 0 degree. So the resistance at any temperature can be found from this formula if you know the initial resistance at 0 degree. Okay, now what is alpha naught? So using this equation, just RT minus R naught by R naught is into T. So I can write the temperature coefficient of resistance is the increase in the resistance, because this is change in resistance. So you can write increase in resistance per ohm original resistance. Okay, this R naught is the original resistance. This temperature is there, so per degree rise in temperature. So this is the temperature coefficient of resistance definition. Let us see the effect of temperature on copper. This is the graph between resistance and temperature. At 0 degree the resistance is R naught, whereas at 100 degree it has increased to a resistance of RT. So if you know the initial resistance, that is resistance at 0 degree, you can find the resistance at any other temperature. That is given by the formula we have derived earlier. RT is equal to R naught into this one. So what is this alpha naught value for copper at 0 degree? It is equal to this one. So what does this indicate? It means that for every 1 degree, this value gets added to the original resistance. Suppose, let me take R naught is equal to, so let me take R naught is equal to 1 ohm. Okay, so in this case, suppose for example, okay, this is 1 ohm. I will write 1 plus this value alpha naught into 1, because at 1 degree, so this is at 0 degree, at 1 degree, so I am writing 1 here. So what it happens, 1 plus 0.004. So this will be your resistance at 1 degree. Okay, so this is the resistance at 1 degree. Similarly, for other degrees you can find. We have seen that if we know the resistance at 0 degree, we can calculate the resistance at any other temperature. But normally, if you take a machine, it will be at room temperature, not at 0 degree. So it is easy to find the resistance at room temperature than at 0 degree. So in such cases, we can use this formula. So R1 is the initial resistance at temperature T1 or room temperature, and R2 is the final resistance at temperature T2. Alpha 1 is the temperature coefficient at T1. Okay, so if you know all these things, you can find, so the same formula you can apply. RT is equal to R naught into 1 plus alpha naught into T. So instead of RT, I am writing R1. So R1 is equal to R naught into, similarly I can find R2 is equal to, what is this? So if I don't know R naught, what I can do is you divide these two. So R naught get cancelled. So from that you can get a relation. Similarly, you can do one thing. The same formula you take it. here RT represents the final resistance. So I will write R2 is equal to R1 into 1 plus. So this value you have to write it here. So this is R1 means here you write it at alpha 1 into change in temperature. So in this case it is T minus 0 degree. So we have taken it as T. So here you can write change in temperature T2 minus T1. So you can find the resistance at any temperature if you know the resistance at any other temperature. You can determine the alpha value from the graph also. So we have already seen R0 is the temperature at 0 degree, RT is the temperature at any other temperature T. So we have this formula alpha naught which we have derived earlier. Let us find the slope of this line. What is the slope of this line? Y-axis divided by x-axis. So y-axis you have RT minus R0 because the full thing is RT whereas R0 is still A. So RT minus R0 divided by this is the temperature T, 0 to T. So the slope of the graph, you find the slope. So now you see in this formula this RT minus R0 divided by T. So this is the slope. So I can write alpha naught is equal to slope of the graph divided by original resistance R0. And similarly for alpha 1 I can write slope divided by original resistance R1. Alpha 1 you have to write R1, alpha naught R0. So now you make the slope is same. So slope equal to equate these two, you will get the relation for alpha 1 and alpha naught. So simplify it, you will get, so if you know alpha naught, you can find what is alpha 1. So this is one of the method to find the alpha values for any temperature. So now the points to remember here are the resistance is the opposition offered by a substance to the flow of electric current. R equal to rho L by A where R will be in ohms. Rho is the specific resistance or resistivity and its unit is ohm meter. L is the length in meter and A is area in meter square. And conductance is the reciprocal of resistance and its unit will be Siemens per meter or mho per meter. We have seen the resistance of the material changes with change in temperature. So there are two type of materials which in which the resistance increases with increase in temperature, that is called positive temperature coefficient. The resistance decreases with increase in temperature, have negative temperature coefficient, and RT is equal to R0 into 1 plus alpha naught T, where R0 is the resistance at 0 degree, RT is the resistance at T degree, and alpha naught is the temperature coefficient at 0 degree. And if you don't know the resistance at 0 degree, you can use this formula if you know the resistance at any other degree. So the temperature coefficient of resistance is the increase in resistance per ohm original resistance per degree increase in temperature. Alpha naught, you can write it as slope of the resistance temperature graph divided by original resistance. And alpha 1, that is alpha at any other temperature, can be found from this formula. So if you want the study material or important points, you can visit this website, and if you like the video, do subscribe to Read Electric Vehicle channel, and if you need any other content or problems on this topic, please do mention in the comment section so that I will include that video also. So these are some of the references.